So now, we need to understand what an hydrostatic force is. So in hydrostatics, we study the pressure that is exerted by the liquid on the surfaces. So we have when a liquid is at rest, it exerts some amount of force, okay, on the surfaces of its containers.
Number first, you.
On the surfaces of the containers. Okay, that was continue. So what was I saying? I was saying that when a liquid is in a container, it exerts first of all some force at the bottom of the container and on the walls of the container. And if you throw, let's say, a piece of metal in a container that is filled with a liquid, let's say for example water, and then it sinks to the bottom, there is an amount of liquid on top of that metal that you throw in the container full of a liquid that will exert some pressure or some force on that particular immensity object in the liquid. Okay, and then that liquid, that force acts at some point on that immensity solid or metal in the liquid. So in our discussion, we'll be just looking at two things. First of all, we'll look at the total pressure on a surface, okay? The amount of pressure that a liquid exerts on an immensity surface. And then we'll look at the pressure position or the point at which this pressure acts on a particular surface. We'll look at the total pressure and the center pressure. The center pressure is the point at which a liquid acts on a solid surface that is immersed in a liquid. So let's visualize this. Like I said earlier on, suppose this surface is immersed in a liquid, and on top of it is a liquid volume of height x bar. Okay, so our question is, how much pressure is being exerted on this surface for the liquid that is above this surface? How much pressure? And then another question is, at what point does this pressure act on this surface, on this particular surface? And as you can see, this is an horizontally immersed surface. It's an horizontally immersed surface. So what's the total pressure for this? The total pressure is given by the area of the immersed surface, then the depth of horizontal surface from the liquid, and then the specific weight of the liquid. Specific weight of the liquid. So total pressure, we can say, is the amount of pressure acting on this solid surface by the liquid above it is given by the weight of the liquid above the immersed surface. I'm reading here. The weight of the liquid above the immersed surface. Okay, so we can write the weight as specific weight of the liquid times the volume of the liquid. We can also split the volume to say volume is the surface area times height. Surface area of the object times the height. So this volume is the volume of the liquid above the immersed surface. So we can find the total pressure acting on this surface by knowing the weight, the specific weight of the liquid times the area of the surface that is immersed under the liquid, that is immersed in the liquid, times the height. Okay, this height is from the surface of the surface of the immersed object to the surface of the liquid. That is how you find the total pressure which is exerted by a liquid on top of the surface. And now when In a case where the object is now vertically immersed, how do you find the total pressure? First of all, you need to take note of two positions on an immersed object. There is the point G and point C. So point G is also known as the center of gravity, okay, or the center of mass. Then point C, it is the center. The point C is a center, or the point where this liquid is going to exert its pressure. Okay, that is the point at which this liquid is going to exert its pressure. It is actually below the center of gravity. And from this point to the surface of the water, we have the height h bar. Okay, from the point at which the pressure from the liquid acts on this object, we have the h bar. And then the gravity, the center of mass, or the center of gravity, the point at which the mass, the gravity acts on this body. From this point to the surface of the liquid, we have x bar. Okay, we have x bar. So the total pressure acting on this on a vertically immersed surface is given by still the same, the weight of the liquid above this, the object, the surface area, and the height from the center of gravity. But what becomes different is the point at which this pressure acts, okay, or the point at which the pressure force is exerted on the liquid surface. So let's go through this point, the center of pressure. So the intensity of pressure on an immersed surface is not uniform. Okay, so when we go back to this immersed surface, okay, on top here, the amount of pressure which is being acted on by the fluids above this object at this point is less compared to the point here, okay, because here, at the bottom you have got more liquid volume pushing at this point, on this point. Then on top here you have less liquid volume acting on this surface, and that's why we have that the pressure acting on the immersed surface is not uniform and is greater at the lower position of the figure. The resultant pressure on any immersed surface will act at some point, like we have pointed out, and it is always below the center of gravity of the immersed surface, and that's somewhere towards the lower edge of the figure. And this point is given by h bar, which is this h bar, this c dot, this height. H bar is given by I naught over a times x bar, where I naught is given by the moment of inertia times the area of the immersed surface times the distance from the center of gravity to the surface of the liquid. And if you substitute this I naught in this formula here, you're going to end up with this formula. So if you are asked to find the point at which the pressure is acting, the pressure of the fluid of the liquid is acting on an immersed surface, you have to know the moment of inertia Ig, the surface area of the immersed surface of the immersed object or figure, and you have to know the distance from the center of gravity of the immersed object to the surface of the water. Then you'll be able to find the point at which the pressure from the liquid is acting on a surface. Now, this moment of inertia differs according to to the shape of an immersed object. So when you look at this table is saying that, let's look at the second row, or the second row, okay, where we have a triangle. When a triangular object is immersed in a liquid, okay, its surface area, we know the area of the triangle is base times height over 2. Then its moment of inertia will be given by the base times the height cubed over 36. So this one, you have to know it by heart. So when we're talking about the triangle, the moment of inertia will be given by this formula. When you're talking about a rectangle in the second row, this row here, the moment of inertia will be given by this formula. But the area we know for a rectangle is base times what do we call the breadth times the width, yeah. And then when the immersed object is circular, the moment of inertia will be given by pi d to the power 4 over 64. And then the area of a circle, we know it's pi r squared, or pi diameter squared over 4. When the immersed object is a trapezium, this is how you find the moment of inertia. Okay, the area for a trapezium is given by this. Let's do an example. Example 1 is saying that a circular plate of diameter 1.2 meters placed vertically in water in such a way that the center of the plate is 2.5 meters below the free surface of the water. So we're talking about water here. Determine the total pressure on the plate, the position of the center of pressure. So they're saying that the center of gravity here, from point G to the free surface of the water, we have 2.5 meters. So we have our x bar. And then we also have the diameter of this object, and we also have information that it is a circular object. So we know the formula for the moment of inertia for a circular object. So for the total pressure acting on this object, the formula is that the specific weight of the liquid times the surface area of the immersed object times the distance from the center of gravity of an immersed object to the free surface of the fluid of the liquid. So we just need to identify what is the specific weight of water. Here we're talking about water. Water is a special liquid because 1 liter of water is equal to 1 kg of water. But this is not true for all the liquids. 1 liter of petrol or diesel is not equal to 1 kg of petrol or diesel, no, because their specific weights are different. But with water, the specific weight of water is actually equal to the gravitational constant, the G, okay, 9.81. Then the surface area of a circle is given by pi d squared over 4. Pi is a special constant over 4. The diameter has been given to be 1.2 from the question. The diameter is 1.2. So you substitute, you get 1.13 meters squared. So substitute your area there. Then the height, x bar, from the gravitational point to the free surface is given as 2.5 meters. 2.5 meters. And remember, the units must be uniform. Must be in SI units. So 2.5 meters substitute, and then evaluate, you get 27.7 kilo newtons. That is the pressure being exerted by the fluid on the immersed surface, which is immersed vertically. Now the position of center of pressure. At what point does this pressure act? We're looking for now C, the point C. At what point does this liquid act on this immense surface? It is given by moment of inertia over area times the height plus the height. Moment of inertia for a circle. We go back to the table. This is our circle. The moment of inertia for a circle is given by this. Okay, this formula. Pi d power 4 over 64. So substitute pi d, diameter has been given as 1.2. Power 4 over 64, you get 0.1018 meter m to the power 4. Okay, then substitute in the formula, substitute that number there. In the area, we found the area already, times the height we know is 2.5 plus 2.5. If you evaluate this, you get the point at which the pressure acts on the image surface as 2.536. 2.536. Before we go to the next example, let me invite some questions. Inviting questions. Yes, class, you are free to ask questions. I hope my mic was working.
Actually, for me, it's not a question, but can we also have this module?
Oh, sure. Yeah, after
Yeah,
class.
I think for practice sake, it might be important for us.
And I'm supposed to give you questions for the previous module that are
Yeah,
based on the previous module.
and also this one is the standard, yeah. The position of center of pressure. That formula you are giving us, that one H bar is equals to
Yes,
IG over. This one is a standard formula.
standard formula for vertically immensity.
Okay.
Yes, standard formula.
Yeah, it's fine. Thank you.
Okay, in the next example now, everything we have an isosceles triangular plate of base 3 meters. Let me just go straight to the figure. I don't know if you are able to see this figure. Let me zoom it a bit just for now. Yeah. So we have this triangle, okay, immersed in this liquid, but the only difference is that this part of the figure is touching the surface of the liquid. And in the question they are saying that this is an isosceles triangle. So isosceles triangle, if this is 3 centimeters, if this is there will be sides which will be equal, isn't it? There will be sides that will be equal for an isosceles triangle. And then we're saying that from the center of gravity to the surface, the height, the distance is x bar. Then from the center of the point where the pressure is acting on this surface, we have h bar. And then the amount of this figure, which is immersed in the liquid, it is 3 centimeters, 3 meters. Sorry. So in the question, like I said earlier on, we are just concentrating on two things: the total pressure acting on the surface by the liquid, and the center of pressure, or the point at which this pressure is acting. And in this question, we're not looking at water this time around. We're looking at oil of specific gravity 0.1, 0.8. So you'll be tasked now to find the specific weight. Specific weight will be given by the given specific gravity times the gravitational constant, the G, the 9.81. So this is given, the specific weight times the specific gravity of oil times the specific gravitation constant 9.81. Multiply that, you get the specific weight times the area of the triangle. Area is given by base times height over 2. So the base and the height are the same. Since this is an isosceles triangle, base and the height will be the same. Multiply that and then you get 4.5 meters squared. Then the x bar for a triangle, we go back to the table to find it. To find the x bar. Oh no, sorry. Yeah, we'll go back to the table. The table has got x as well. You can go to the table to get our x bar as well. So you're going to have 1 over times the height. 1 over 3 times the height. 1 over 3 times the height, we're going to have 1 meter. Then specific weight is this one, we've already found it. And then evaluate this, substitute and evaluate, you get 35.3 Newton-meter for the pressure. So this is the amount of pressure which is being acted on this mixed surface for this
Sorry, sir.
triangle. Yes?
Sorry. Why are you saying that the x bar is equals to 1 over 3 times height?
So we're going to find the height from this point to that. For a triangle, these formulas have been given already. For a triangle, this is the formula here. Okay? In the first row, x is equal to h over 3. So this is supposed to be your x bar. These x's that are here, this is your x bar. The center of gravity, for the center of gravity. So next time we'll be talking about the point at which the pressure is acting. We'll look for the moment of inertia. For a triangle, this is the formula here, b times h cubed over 36. So substitute our base and our height, which is 3 in our case. Okay? Hello? Okay. So at what point does now this pressure act, or at what position is it acting? So h bar will be given by the moment of inertia over a times x bar. Moment of inertia now for a triangle is given by base times height cubed over 36. So substitute your base and your height in this formula, you get the numerator there. Then the area has been found, and there's a problem here. Why do I have a 1? Oh, it is a 1 actually, yes. It is 1. This has been found to be the 1, the x bar has been found to be a 1. So 4.5 times 1 plus 1, then simplify everything here, you should get 1.5 meters for the height, for the point at which this pressure is acting on the given surface. Okay, so the next one we're going to talk about is when the immersed surface is at an inclined
Sorry, sir.
position. Yes.
I was kindly asking if you can simply just scroll down on the table. I'm trying to follow on this. I think should be Amion who asked that. Why is it 1 over 8, 1 over 3? So here it's saying the x bar is just h over 3, not so.
Yes.
Now, if you go to the example, the one that we are just from doing for the triangle.
Yes. Let me go back.
Sir?
Let me go back to the example.
Yes, sir. Yeah, here now on the example on x bar, it's saying 1 over 3 multiplied by h again. I thought the h is the one that is supposed to be h on top over 3, you find x bar.
H on 2. You're talking about this.
Yes, sir. On the table, we're saying that x bar is h over 3. So h here,
Or it's like it's on the side. That one.
yes. So no wonder I'm confused, because if you follow this one saying 1 over 3 multiplied by 3 again, so the 3, which means is for the height. Yes.
Yes, the 3 is for the height. But
So
if you understand that for a triangle, x is given by h over 3. Remember, 1 over 3 times h is same as h over 3. Hello? Remember, 1 over 3 times h is same as h over 3.
yes.
So now this h is this one here, the 3. So this 3 is coming from the formula, and then this 3 is coming from the problem. Please
So now,
express yourself. Yes.
yes, now. So I'm trying to get the formula, because the standard formula from the table for the x bar is just h over 3.
Yes.
So which is basically, yes, which is h over 3. So now here we've got, it's like the formula for x bar is 1 over 3 multiplied by h, according to this example here. So that's why I'm a bit lost, because
yes, so it's the same thing actually. H over 3 and 1 over 3 multiplied by h is the same thing, because look at this. If we were to multiply this 1 times h, we're going to have h over 3.
yes, that much I know. Now, where I'm getting confused now is we're getting the other 3 this side, where from here 1 over 8, 1 over 3 multiplied by h. The follow up is this same 3 that you've highlighted now.
Yes.
May I come in? May I assist?
Yeah, sure.
Okay. Yeah, if you look on the formula as he's saying, the formula it's h over 3. Then what is the value of h? The value of h is 3. That h, it's h over 3. Yes, it's correct. That's the formula. Then what is the value of h? Just go and substitute the value of h there. You will get 1 over 3 times 3, which is equals to 1.
Exactly.
I think it's clear.
Oh, okay. I get now. It's basically 3 over 3.
Yes, basically 3 over 3.
Okay, so.
Okay. So remember, this lesson has got only 2 things: the pressure and the point at which the pressure is acting. So now let's look at for inclined objects. When an object is immersed in a liquid at an angle. Okay, as you can see, this object which looks like a football, a rugby, that's rugby football. Okay, it is tilted at an angle theta. So how do you find the total pressure being exerted on this object, and also the point at which this pressure is acting, the C? How do you find that? First of all, we discover that for the total pressure acting on this object, the formula will be the same. The weight of the liquid, okay, acting or pushing on this immense surface times the surface area of the immense object times the height from the center of gravity to the surface of the liquid. So the pressure is actually the same, whether inclined or not. What's different is the point at which this pressure will act. So the angle is going to affect the point at which this pressure will act. And the formula now will be given by the moment of inertia times sine squared theta, where theta is the angle of inclination or the amount of tiltness. Yes. So the only difference here is now we're considering the angle. Remember, when for objects that are horizontally or vertically immersed, which means that they are at an angle of 90 degrees. And sine 90, we know from trigonometry that sine 90 is actually 1. And that's why we couldn't see this sign on the previous examples, this sine theta squared here. Okay? But for inclined immense objects, just remember you have to include the angle. You have to consider the angle. So the only difference is this sign here. Moment of inertia times sine squared theta. So let's do an example for an immensity object, for an object which is immersed at an inclined angle. So the question is saying that a 1 meter wide and 1.5 meter deep rectangular plane surface lies in the water in such a way that each plane makes an angle of 30 degrees with a free water surface. Okay, so this is a triangle. Sorry, this is a rectangular object immersed in this liquid at an angle 30 degrees. Determine the total pressure and the position of the center of pressure when the upper edge is 0.5 meters below the free surface, below the free water surface. So this point, this edge up to the surface, it is 0.5 meters. So for the total pressure, you know the formula is the same. The pressure will be given by the weight of the liquid, the specific weight of the liquid times the surface area of the object times the distance from the center of gravity to the surface. Okay, that much we know. So here we have the area can be found of a rectangle. The specific weight of water, we know it is equal to the gravitational force, the gravitational constant. But the challenge is the distance from the center here to the surface. So here you're going to resolve the angles. We're going to resolve the angles. We're going to say this distance from here up to there. Okay, suppose this point is translated to the entire object here is translated, reduced to this problem, to this thing they have written here, which has been written here. They're saying that from here, suppose this G is at this point, okay? This G is at this point. So from here to there, we are going to look for LM. We're going to look for LM. So LM will be given by LU plus UM. LM will be given by LU plus UM. And that is this should be the distance x bar. So now to find the LU has been given as 0.75, but UM hasn't been given. So how do you find UM? Okay, when you draw this triangle here, we can use trigonometric ratios to find this base here, and remember the center of gravity acts at the center of an object. So meaning from here up to there is only halfway of this 1.5. So from U to N, we know the distance. And then the angle inside here, we know it is 30 degrees. Because this line UN and the surface of the water, they are parallel. So the angle inside this small triangle and this angle here are the same. And this one has been given to be 30 degrees. So this one should be 30 degrees as well. So we know one angle we know one side, we are looking for its opposite side. And that's where XL, trig ratios will come in. So L, it will be LM plus MU. LU has been given to be 0.5 plus MU. From trigonometric ratios, we're going to have MN times sine 30 degrees. MN times sine 30 degrees. That's how we're going to find UM. And MN is only halfway of 1.5 meters. So NM is only half of 1.5 meters. So evaluating these now, okay, evaluating everything here, you get 1.125 meters. And then you substitute your X bar here. Substitute your X bar there, the 1.125. Then the area of this rectangular figure is 1 times 1.5. 1.5 times 1 is what we get here. Then evaluate, you get 16.55 kilonewtons for pressure. So now the next thing is, at what point does this pressure act? At what point? With the center of pressure. So the center of pressure, the formula is that the moment of inertia times the sine of the angle of inclination over everything else here. So the angle has been given to be 30 degrees. So sine 30 degrees squared times the moment of inertia. So the moment of inertia for a rectangular figure, you go back to the table. You go back to the table to get the moment of inertia for a rectangular figure. Rectangular figure, the moment of inertia is this. BD times cubed. Okay. So in our case, the one of the sides is 1 and then the other side is 1.5 cubed over 12. So 1 times 1.5 cubed will be equal to 0.281 meter to the power 4. Then substitute this into this formula. You are going to end up with 1.166. And that is how you find the pressure and the point at which this pressure acts for an inclined or a tilted immersed object. Yes, any questions? And remember, this was water. For non-water liquids, you'll be given the specific gravity so that you can find the specific weight, just like in one of the examples. Yes? Any questions on that? I hope I was recording. Any questions, class? Hello, are you there?
Yes, we are there, sir. So is this the end of the syllabus?
No. It's not the end of the syllabus. This is just the no.
Oh, with all these calculations, you are still going.
Yeah, we're still going.
You want to kill us with this calculation, differentiation,